Gravity's ultimate endpoint is an absolute trap. When giant stars collapse, they compress their mass into a point so dense that not even light can escape its pull. We watch black holes swallow entire stars, tearing them apart and pulling the material past the event horizon. But physics tells us that matter and energy cannot simply vanish. They have to go somewhere. General relativity describes a second mathematical solution to this disappearing act, the white hole. Einstein's equations allow for a region of spacetime that fiercely ejects matter and energy. It is surrounded by an event horizon that acts as an impenetrable wall, preventing anything from the outside from ever entering. In the math, there is no structural difference between the two. The geometry of a white hole is just a black hole with the flow of time reversed. A black hole is a sink, funneling water down the drain. The white hole is the result of running that tape in reverse, to watch the water erupting back into the room. But here we hit a massive physical contradiction. We have documented proof of black holes. We have photographed their event horizons. Yet when we scan the night sky for white holes, objects that should be incredibly bright as they expel matter, we find absolutely nothing. This paradox forces physics into a corner. Either the mathematical foundation of general relativity is incomplete, or white holes do exist in our universe, but they are hiding in plain sight. To solve the missing hole problem, theoretical physicists turn to loop quantum gravity. This framework proposes that space-time isn't a smooth, infinitely compressible sheet. Instead, it is granular. Space itself is made of tiny, indivisible building blocks, creating a physical limit to how tightly matter can be packed together. When a dying star collapses into a black hole, it compresses until hitting that absolute quantum limit. The matter cannot squeeze tighter, acting like a compressed spring. It rebounds outward, turning the black hole inside out, instantly becoming a white hole. Why haven't telescopes captured these violent explosions? The answer is time dilation. Immense gravity warps time. Inside the core, the bounce takes a fraction of a second, but for an outside observer on Earth, that exact process takes trillions of years. We haven't failed to spot white holes. Our universe is simply too young. Even the very first black holes formed after the dawn of the cosmos haven't had enough time to reach their detonation point. But we might be looking for the wrong size of explosion. What happens if we stop waiting for small black holes to erupt in the future and instead look billions of years into the deep past? A growing framework called shockwave cosmology proposes that the Big Bang was a singular, massive white hole explosion. The math aligns perfectly. A white hole ejecting a massive amount of dense matter and energy from a single point perfectly mirrors our rapidly expanding early universe. It acts as a timeless window, birthing material into existence. This Penrose map shows a black hole to white hole transition. It illustrates gravitational collapse hitting a quantum limit and rebounding. Space-time lines don't break. They seamlessly extend outward, mapping the birth of a new baby universe on the other side. If this model holds true, our entire observable universe, every galaxy, star, and planet we can see, is the interior of a massive cosmic rebound. Theoretical math and thought experiments are fascinating, but physics requires empirical proof. Scientists are now moving towards observational data to finally detect these gravitational ghosts. They are looking for specific ripples in the fabric of space, known as stochastic gravitational wave backgrounds, or SGWB. If a massive white hole bounce occurred, the physical force of that rebound would leave a permanent, vibrating imprint on the universe. This graph models the expected gravitational wave background from a white hole. Notice the exponential decay curve near the 10 MHz frequency mark. This precise cutoff distinguishes it from standard cosmic noise, perfectly fitting the detection band of the upcoming LISA Space Observatory. But gravitational waves are only half of the required proof. Researchers also need to find corresponding temperature and polarization imprints etched into the cosmic microwave background, the oldest light in the universe. They are hunting for patterns called B-mode anomalies. This chart maps the detection ratio of simulated B-mode signals. The vertical dashed line at an angular scale of L equals 200 marks the exact spot where white hole perturbations would peak, creating a signature that differentiates them from standard inflationary models. This final plot illustrates the computational cross-correlation between the LISA gravitational wave data and the cosmic microwave background B modes. The pronounced peak at L equals 200 shows a direct statistical tie between the physical ripple in space and the ancient light of the cosmos. Detecting this exact dual signature is the ultimate litmus test. It is the only way to finally distinguish a real white hole from empty theoretical mathematics. With advanced detectors coming online, the search for white holes moves out of the realm of thought experiments and into the era of data-driven astrophysics. Finding these combined signals would prove that black holes are temporary states, cosmic recycling centers that process and redistribute energy rather than destroying it forever. Proving white holes exist would reveal a universe where destruction is inherently tied to creation, offering us a verifiable glimpse into the mechanics that shaped our Big Bang.